तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Hello and welcome. In this final session on Introduction to XML, we shall be delving primarily into XML databases. That is, until now we have been talking about what is XML and what are the benefits of XML or data interchange using XML and XML queries or schemas and so on. But today in this session we shall be looking into XML databases and what are the issues that that come up when XML data has to be stored or transmitted and exchanged over pre-existing or some set of existing data stores. We shall also be looking into the larger problem of what is called as semi-structured data management. Semi-structured data, as you might have imagined from the name, is data which do not have specific rigid structures. And we shall show that more and more the data requirements of today's world, what we call the post-internet world, is being defined by semi-structured data rather than structured organized data. And semi-structured data poses some unique problems, in fact some fundamental problems in database management. And what we shall do here is that we should in this session is we shall only motivate those problems rather than providing any solutions as such, many of which are in some sense areas of active research. And so we shall be motivating the problems with some examples or some analogies and instances, and we shall conclude this session with a list of what one could expect in terms of semi-structured data management. So let us proceed further with this session. And as with the earlier session, some of this material have been derived from an invited talk by Jayant Haritsa in the VLDB summer school held in Bangalore in June 2004, and of course including many of the analogies and jokes that have been there in the slide. So here's an acknowledgement for those set of material that have been derived from those slides. So let us look back at XML again and recap what we have learnt about XML and what are its characteristics. First of all, before we look into the points on the slide itself, let us remember that XML is a platform independent, standardized and extensible markup language. So in a sense that it's platform independent because it is written in character data, and every platform is should at the very least support character data, and it's an extensible markup language. That is, it does not have a specific set of keywords as such. I mean, of course it has keywords where you say very good declarations, but for describing the data itself, it doesn't have any keywords. The user who is describing the XML document can come out with his or her own set of tags or metadata that describe how the data is organized and how what semantics to attach to each data set in this in an XML store. And XML syntax has a plain hierarchical structure which is easy to navigate and easy to enforce and easy to parse as well. So we have as a result we have query languages like XPath which translate an XML query into a directory like path expression, which is quite intuitive for users who have been using computers, and so to traverse directories and look for something in a specific directory and so on. And last but not the least, XML is understandable or parsable by both the machine and the computer. So if everything fails, what you can do is just open an XML document in Notepad or VI or Emacs or some such text editor, and look through the document and see where there could be a problem, especially if maybe a starting tag doesn't have an ending tag or some problem of that sort. So and of course there are issues like what about the amount of space, extra space that XML takes up, and this can be answered by the fact that one need not store XML in character form on disk. You might want to actually compress XML data and then store it on disk, so that you can and decompress it when reading it, so that the actual disk space that is taken up by XML is reduced. So let us address the question of data interchange now using XML. XML is said to be a platform independent source of data representation and representing data that is self-describing, in the sense that the metadata is embedded within the data. Now, but what is the problem? What is and of course the advantage of this being that you don't have to worry about whether the end user is using the same platform as yours. If you are using Linux, the end user could be using Windows or Solaris or Mac or whatever, and the end user could still use your services using SOAP or some other form of XML based message passing protocol, and you can still answer or you can still provide those services via an XML wrapper. But what is the interchange problem actually, or in its entirety? For the interchange problem, we have to first note that most data is already stored in some existing databases. It's quite unlikely that databases that have been existing for large periods of time now will be replaced by an XML data store, or will be replaced by something else that is unifying. So databases are going to continue to exist, and the question of data interchange will boil down to the fact that how to interface these databases using XML or using a common interchange language. And databases will not only exist, will be updated through existing interfaces. It's again quite unlikely to expect that all updating and all interface to the databases will come through a common interchange format. So what is really required is to provide XML wrapping to existing databases, and SOAP, for example, is SOAP is an example in this regard. That is, message passing between objects existed long before XML came into the picture. There were several different object middlewares like Corba or DCOM and so on, which supported message passing between objects over a distributed system. And but however, one needed to be Corba compliant in order to be able to, a platform needed to be Corba compliant in order to be able to support Corba. That is, Corba had to be written for that platform. On the other hand, when using XML, it does not bother about what kind of platform that's being used, because every message is passed using an XML wrapper. So SOAP is some kind of a generalization over message passing frameworks in distributed object-based systems, which has been extended from simple small distributed systems like Corba to a larger web-based services like using SOAP. So a similar analogy also exists in data integration, where data exists in different databases in pre-existing forms and pre-existing applications, and they have to be integrated by wrapping the data around using XML wrappers. So one simple way to convert databases, and now here we are assuming relational databases, and for the most part you would be correct, because majority of the database implementations around the world are relational databases. So assuming that existing databases are relational databases, and we need to be able to interface between these different relational databases, which are across different platforms. A simple way to perform this is to convert relational tables in their canonical form to XML documents, and this slide shows such an example, where there's a slide called actors containing of two different columns, last name and first name, and this table became one XML document, actors and /actors. It's a rooted XML document, and it is some kind of a flat XML document in the sense that the number of levels in this document is fixed. That is, the actors file or the actors document comprises of several children called row and /row, where each row comprises of again several children, each child corresponding to a specific attribute or attribute name, and this is the attribute value within the attribute name. So it's quite simple to map a given relational table onto a canonical flat XML file, and given a flat XML file, it's again straightforward to map it back into a relational table. Now let us come to the question of storing XML documents itself, that is having XML databases itself. In many cases, for example in several commercial implementations, Oracle 9i and DB2 and so on, the database gives an impression that it supports XML storage on and XML based updates. However, what it actually underneath it is still a relational database, and then there is an XML wrapper around the database. However, that is not. There are several other approaches to storing XML documents, and in many cases it becomes necessary to treat XML not just as an interchange language, but also as the language in which data is stored. And some of the issues that occur in this regard would be issues like data layout. How do you organize the XML data? There are again many alternatives to this question. One can map XML data onto a relational database, or one can map an XML data set as a special kind of object in a object relational database, or one can store XML data in native XML form or in text form and so on. And what about updates? I mean, XML databases are prone to updates, and both and here in XML, unlike in say a relational database, it's not just the values of attributes that can change. The actual structure of the database can also change very frequently. In a relational database, we basically assume that once we fix the schema, it is intact, and it's only the data sets that are updated. That is, new attributes are added, or existing attributes might be deleted or modified and so on. But the evolution of the schema itself, that is change in the structure of the database itself, is considered to be far less frequent, if at all it happens. And so the database is modified, database is oriented, the relational database is oriented towards fast updates and retrieval of data and not the structure as such. But in an XML database, that may not be the case. That is, there could be updates of not just the values, but also of the structure in which data is stored in the database. And in many cases, there may be no explicit schema that's available. So well-formedness itself is the schema. So we don't really know which is a valid structural update and which is an invalid structural update, and what kind of constraints exist between different elements and so on, unless there is a XML schema or a DTD that's available for us. Similarly, there are different kinds of query supports that need to be supported by an XML database. The standard flower queries that we saw earlier, where for, let, where, return kind of queries, and also select, project and join based queries, where which is also supported in XQuery, in addition to recursion or document construction, that's transformation from one XML document to the input XML document to the output XML document. And a far bigger problem is of indexing. How do we maintain metadata, or how do we maintain indexes into an XML store such that we can retrieve elements as quickly and efficiently as possible whenever required. And it's not just the normal attribute and value index that we need to store, but we also need to store full text indexing, what are called as inverted indexes. So to be able to search full text elements or data sets quite efficiently. In addition to these kinds of indexes, we also need what are called as structural indexes. I mean, structural indexes essentially talk about what are the relationships between structural relationships between different elements. Is one a child of the other? Is one reachable from the other? Or what are the siblings of a given element, and so on. And in addition, there are general requirements like scalability and recovery in case of failures, concurrency control, updates and during updates, and so on. So let us look at XML storage structures itself, and what are the different kinds of choices we have for XML storage. Basically, we can divide the different kinds of XML storage, that storage structures that are storage paradigms or storage mechanisms that are available into three different classes. What might be termed as flat stream based storage, or native XML storage, and colonial storage. So what do each of these terms mean? A flat stream based XML storage essentially stores XML data as some kind of objects in an object relational database. They are stored as clobs, or remember what is a blob. A blob is a binary large object, and a clob is a character large object. So you just store an object comprising mostly of characters, so a character large object which contains its own mechanisms of access and retrieval as one of the attributes in a relational database. So just like storing any multimedia object or some such object, you can store an XML data set in a relational database itself. But of course, the advantage of this is that you don't need to reinvent anything, in the sense that there are several object relational databases that are already available, and it's just a question of using one of the object relational databases to store XML documents. But however, of course, the flip side of this argument is that the database itself does not support any XML centric queries. So you can query the database based on object relational constructs, but not an XML construct itself, and all those XML specific query constructs like flower queries or XPath queries and so on cannot be directly supported. The next kind of database storage strategy for XML is the native XML storage. Native storage essentially means that you design a new database from scratch for storing XML data, optimized for storing XML data. So here you have to worry about everything that that you thought about, let's say, for designing a relational database. One needs to think about the storage structure, block accesses, that is the physical storage structure, indexing structures, then some kind of query mechanisms and recovery mechanisms, concurrency control, transaction throughputs, and how to maintain efficient transactions and so on. So everything that goes into designing any conventional DBMS should go into designing this native XML storage as well. So and there are quite a few examples of databases supporting native XML storage. The third strategy is what might be termed as a colonial strategy. A colonial strategy essentially means that colonize an existing paradigm using XML, that is use some kind of use an existing paradigm like say a relational paradigm, and then map every XML construct to a relational construct, rather than note the difference between a colonial strategy and the first strategy, which just put XML storage as character large objects or one of an attributes of a relational table. However, a colonial storage essentially decomposes or deconstructs an XML document into relational constructs and reconstructs them back. So whatever XML related query that you provide, like XPath expressions or flower queries and so on, they have to be rewritten in SQL, and you have to have a mapping. One needs to have a mapping between XQuery constructs and SQL constructs, and vice versa. And of course, this can be both an advantage and a limitation. The advantage primarily being that you don't have to worry about a number of techniques that the native XML storage has to worry about: storage structures, blocks, storage structures, concurrency control, and recovery, and so on. However, there's a significant, if not huge, performance overhead in terms of mapping an XQuery construct into an SQL construct, especially when there's a recursive kind of query that's given. Mapping it into an SQL construct can take quite a while, and running the SQL query on the database can also be quite inefficient. And so let us look into the second strategy in a little bit more detail, namely the strategy of native XML storage, that is redefining or redesigning an XML database by looking at all the different aspects that needs to go into an XML store. So what are the issues, what are the typical kinds of issues that one needs to worry about when designing a native XML storage? One needs to think about data layout. How is data organized on the disk? And physical data layout is essentially, that is, if my disk is organized in terms of pages, disk pages or disk blocks, what should each block contain, and how should the blocks be organized, and so on. Indexing is again a major requirement. Like we said before, it's not just attribute and value indexes that are important. We need to also look into full text indexing, or indexing of phrases within text, or structural indexes that talks about how elements are related to one another, and so on. And it needs to also address query support. What kinds of queries are supported in this store, and how do we optimize queries, and how do we pre-process? Do we need to pre-process, or if so, how do we pre-process for managing efficient query retrieval, and so on. Then access control, concurrency control, updates, and so on, transactions, recovery, and so many other issues. Now let us look at the let us look at the question of data storage in a little bit more detail, and what are the different approaches that are used for managing or storing physical disk blocks, or managing the physical data storage. That is, how is an XML tree mapped onto physical disk blocks. Essentially, one can think of essentially an XML data set is a tree. So this slide shows a particular tree like this, where there's an IMDb at the root node, and there are different show elements in the second node, and each show element has different subtrees like title, year, box office, and so on and so forth. So and finally the leaf node contains the data set that is available in this XML tree. Now how do we divide this tree into physical data blocks, and which kind of division makes sense? One way to think of, one way to look at dividing a tree into disk blocks is to cluster trees based on subtrees. That is, this show subtree would go into one disk block, and this show subtree would go into another disk block, and the IMDb would just be in an index which in turn just stores pointers to each of these disk blocks. Now what is the advantage of such a storage? The simple advantage is that the entire subtree is in one disk block. Hence, if I'm if I'm looking at navigational queries where the user just navigates from like opens a opens an element and looks at the subtree and opens another element underneath and looks at that subtree and so on, like in a explorer kind of file system navigation. For such kinds of navigational queries, this storage structure is very efficient, because when the user is navigating, the navigation path is quite close to the actual way in which in which elements are related in the tree itself. It is quite unlikely that the user would open this subtree and start navigating here. So in one disk access, one can read an entire subtree. However, there is a flip side to this to this kind of to this kind of data access itself. Suppose the user gives a X query user gives a query saying show me all elements, show me all show elements where the title contains whatever the fugitive or something like that. Okay. Now if the query has to be searched on a particular element, like say title, and even though we know which element has to be searched for, we still have to access every data block in the disk, because every data block which contains the show element, which stores the show element, would contain a title element. So we still have to access every data block containing the show element in order to access such a query. So so to answer attribute kind of queries, such a kind of organization is a file organization is actually counterproductive, or is not very efficient. However, for answering navigational kind of queries, such a kind of access is quite useful. The second kind of database storage structure is to cluster similar elements within a database, within a data page, that is within a disk block. So this slide shows such an example where the same tree is taken, IMDb and show and title, year, seasons and so on. However, rather than storing an entire subtree within a data block, here each element each element at a particular level are clustered together. So all title elements are clustered together and are stored in one data block. So in the red data block, let us say, and all year elements are clustered together and stored in one single data block, that is a blue data block, and so on. And then there are pointers that point to each of these data blocks, and so any of these elements that don't contain C data or PC data, you can cluster all of these into one data block and then maintain pointers from them to each of these data blocks. Now again, this is in some sense the dual of the earlier mechanism, where such a kind of organization is very useful or very efficient for answering attribute queries. So if I want to say show me all show elements, or return all show elements where the title contains the term the fugitive, then all that you need to do is to first access this block which contains the show element, and find a pointer for the data block containing all the title elements. And with just one data block access, for one will and of course one or more, I mean depending on how many title elements are there, but generally with far lesser data blocks than that are necessary in the previous case, we can access all title elements that are there in this XML store. So answering a attribute query is far simpler. However, answering a navigational query becomes difficult in this case, and there are other techniques for this thing. It depends on how something is clustered. If clustering is performed based on what may be termed as the lowest level elements, where the elements contain just C data or PC data, it becomes difficult to navigate. That is, from show you need to open a title and year, and from title to year it requires a different different block access and so on. However, it might be possible to cluster based on paths rather than based on single elements. So rather than clustering similar elements, some other techniques cluster similar paths. Therefore, one would say that cluster all paths of the form IMDb show on title in one block, and all paths of the form IMDb show on year in another block, and so on. So there are different variants. However, if one were to ask the question, which is the best way of storing, which is the best storage structure for XML databases, the answer would be it depends. Essentially, there's no single there's no single technique that can that is universally most efficient way of accessing or storing XML databases, and to a large extent it depends on what kind of queries that you expect from the users. So if it is navigational queries, it might be better off to cluster the tree based on subtrees, so store subtrees within data blocks. On the other hand, if it is more of attribute searches or even say full text searches, it might make sense to cluster similar elements in a page rather than subtrees. Let us look into the problem of indexing XML documents and what kind of indexing requirements arise for XML documents. Firstly, we said that in addition to attribute value indexing, for which we can use traditional RDBMS indexing like say B plus tree or a B tree, here we need two other kinds of indexes. One is what may be termed as full text indexing, where we should be able to efficiently search on free text data that are written within an XML document. So one might just write a paragraph within an XML document and be able to search for some keyword in that paragraph. And a very common mechanism of indexing full text is what is called as an inverted index. An inverted index is very similar to what you would find at the end of a book, like say a textbook, where you have an index and there are certain keywords, and if page numbers or section numbers in which the keywords are in which those keywords are either defined or used or whatever. So an inverted index on an XML document would index different keywords that appear in the document, and then maintain links into the XML document saying where each of these keywords can be found. And keyword based indexing can be of two kinds. It may either be an XML aware keyword indexing or an XML unaware keyword indexing. So what is the difference between the two? XML unaware keyword indexing just looks for keyword searches. So you just give a keyword search called the fugitive or Jerry Seinfeld or whatever that appears in the XML document. And keywords are searched. This table here shows an XML unaware keyword searches. That is, for every term that appears, it just stores the document reference, which document contains this, or probably the element reference or whatever. So it doesn't bother about where a keyword appears, and it only bothers about the keyword and the value in the keyword. On the other hand, an XML aware keyword or an XML aware index not only contains the keywords, but also another element or another column which says in which element does the keyword appear from. So there is one more index that this ampersand T1 here is an element index or is a key into an element index. So where it identifies each element uniquely in the that is present in the XML store. So what this says is that the term fugitive can be accessed, or the term fugitive appearing in the element whose key is T1 can be accessed using this pointer. So from wherever. So if we are looking at attribute based searches and we want to say return all show elements where the title sub element of show contains the term the fugitive, then an XML aware indexing makes much more sense than XML unaware indexing. And of course the flip side of XML aware indexing is that as the number of elements increase and keywords are repeated across different elements, there is a huge amount of combinational choices that appear between a given term and an element pair. So the term 1993, for example, may appear in different kinds of elements. It might appear in birth date, it might appear in release date, it might appear in show date or whatever, and so on. So different kinds of elements. So each of these have to be indexed separately, and which leads in an increase in the size of the index structure itself. So this table shows different native XML databases that are available, and quite a few of them are already available, like Xylem or Natix or GoXML and so on, and most of them have been built from scratch, and some of them like Exelon or Tamino have been built over existing databases. So it's not in a pure sense a native XML storage, but they do they're called native mainly because they do address many of the questions that are typically addressed in native XML storage, and there's a wide diversity or a wide diversity in the kind of features that are supported. So Xylem, for example, supports full text searches and XPath searches and XQuery searches, but it doesn't have any what kind of APIs that it provides are unknown, and Natix doesn't support any of this, but just support some low level primitives and so on, and there's partial support for XQuery and so on. Let us now move into the second part of this talk, where we look into managing semi-structured data. So until now we have been looking primarily into XML, and XML is a very comprehensive tool to manage semi-structured data, and so what is semi-structured data, and what is the significance, and why is it important to study about semi-structured data. So let us first define what is semi-structured data. There are several different definitions, and of course semi-structured data, what we understand offhand is data whose structuring is not rigid, and data which doesn't conform to a very rigid structuring mechanism. There are other kinds of definitions as well, like data that is inherently self-describing and self-describing data. So with no rigid schema, which basically implies there is no rigid schema, that the data itself defines its schema, and that is known as semi-structured data. And again, data which are generated offhand and without planning and so on, they are also called semi-structured data. Now in today's world, semi-structured data is getting more and more prevalent, and data structuredness is becoming much harder to impose and define and impose. For example, what is the structure of the World Wide Web? I mean, the World Wide Web is a huge data store, but without any structure. In fact, one cannot even say that it is an unstructured data store, because there is some semblance of structure that is present. Like one can think of some metadata tags that are available for each HTML text, some href hyperlink references and so on, and directories and so on and so forth. So, but on the whole, it is not possible to define a specific structure and then impose this structure on the World Wide Web. So the World Wide Web is the best example for a huge semi-structured data store, and most semi-structured data stores are characterized by rapid or dynamic changes or very frequent changes to the data set. So not only is the data not defined a priori, or the structure of the data not defined a priori, it is also changing dynamically, or it's also changing rapidly, and it is not it's not possible to formalize semi-structured data using a nice formal model like the relational model, and the best data structure that's used to formalize semi-structured data are usually graph structures. And there are several different examples for semi-structured data, like web information systems and digital libraries, or even data integration from heterogeneous data sources can be considered to be a semi-structured data problem, where there are several different databases that are already defined, and there are so many such databases that it becomes impossible or impractical to be able to impose a common structure over all of them, and it is easier to treat them as a large semi-structured data store. So a very common example of semi-structured database is of course the Internet Movie Database, which we have been seeing continuous examples of when we are talking about XML as well. So IMDb is a classic example of a collection of semi-structured data, and even though I mean, what makes it semi-structured? The fact that even though it just stores information about movies, each movie is different from the other, and each movie may belong to a different genre. It may belong to a different country. Some may have language fields. Some may have some star cast fields. Some may have some other kinds of fields which may not be available in the other, and so on, in other records and so on. So let's consider an example from a movie database. Let's say IMDb is the database, and of course IMDb not just stores movies, it also stores information about TV serials and documentaries and other such movie related or movie like data that have been released. So even within a movie, let us say even within the movie category, different movies could be different. Movie 1 may have information about the cast and the director in the movie, and who could be the cast and the director, but movie 3 may have something called actors and actresses, where it may make a distinction between who is the actor and who is the actresses, and the direction, that is rather than just the director, it can talk about a direction team or where who directed it and so on. So the structure of each record that makes up a movie movie element in IMDb may be different from one another. And some data elements may annotate more information than others, and some may have missing fields, and the kind of relationships that exist between each of these different elements may also change, may also vary between different records. And in addition to that, in addition to changes in structure, the way in which data is organized itself could change. For example, one might represent an actor's name as first name comma last name, and one might represent it as last name comma first name, or one might or some other record might have it something like just a name, and so on. And data gets added to this database dynamically, and as a result, it dynamically and from different sources, from different independent sources. So it becomes difficult to enforce a particular kind of schema restriction on this database. So what is the problem here, or what is the main problem in managing semi-structured data? The main problem is trying to ascertain what structure or what is the common structure to use for different data sets that are being added to the database, and to be able to formulate queries and formulate query languages and so on. And in addition, we should also note that the structure of data elements is implicit. So it's not that the user providing the data set first defines the structure and then provides data according to it, but structure is embedded within the data itself. Now the structure has to be first discovered and then a common structure has to be evolved over the entire data set. So and this is what is called as the problem of discovery of structure. That is, the structure should be discovered such that the structure is indicative in nature rather than constraining in nature. That is, the common structure that evolves out of a database should not constrain the database to adhere to a specific structure, but rather should be indicative of what kind of data is available in the database and how they are interrelated to one another. Oops, the change in. So here is an example. This slide shows an example of what is the main problem in or what is the main challenge in semi-structured data. In relational or what might be termed as traditional data management, what really happens is you have a UOD or a universe of discourse like a company or an academic institute or university or whatever, and then you have a model of the UOD. That is, there is a schema that defines how data in the UOD should be organized. It's not is organized, but how the data should be organized. And data that is collected from the UOD is first taken through this model and populated into the database. So when we say that an employee should have a PAN number as the primary key and name and dependents and salary and so on, it's only those sets of data that are extracted from the UOD and then sent into the database. And especially, for example, if an employee doesn't have a PAN number and the PAN number is the primary key, then it is not possible to add that employee record into the database because the primary key has to be not null. It has a not null constraint and so on. So constraints are enforced when the database is being populated, right? And the query also is formulated within the model of the UOD. So the query just takes the model of the UOD and queries the database accordingly. However, in what might be termed as the post-internet data management, which is the main problem with semi-structured databases, the universe of discourse, whatever is the universe, the World Wide Web or the Internet Movie Database where users can independently add movie data into the database, the universe directly populates the database. It doesn't go through any common mental model by which the database is populated. In fact, there may or may not be any mental model here as to how the data is organized, but the data is directly populated by the UOD. Now the query, when the query is searching the data, it should not only know what data to search, it should first try to find out what is the mental model or how is the data organized, what is the schema for this by which the data can be searched. So that is basically the schema discovery problem or the implicit schema discovery problem. And in addition to that, the schema discovery problem often encounters the problem of what is called as a large schematic structure. That is, even when we discover a schema, this is again called the maximalist world notion in contrast to the minimalist world model of a traditional database system. In a traditional database system, whatever is not allowed by whatever is not explicitly permitted by the schema is forbidden. So everything is forbidden unless explicitly allowed by the schema. So it's a kind of exclusivist data model where things are thrown away unless they are permitted. However, in a schema discovery process, it's an inclusive model where everything should be permitted unless unless it is sure that it is forbidden. That is, unless it is sure that some kind of a relationship cannot exist, all kinds of relationships between data elements are permitted. So it is not, one cannot a priori define what kinds of relationships exist between data elements, unless of course we know that some kind of relationships do not exist in the database, or cannot exist in this UOD, right? So the associated problem from this is that the discovered schema can be quite large, in contrast to a relational schema where the schema is much smaller than the data set itself. So in the internet movie database, for example, we might discover that there are a lot of different things that go into a movie based on what people add into the database, and we should allow for all such relationships unless of course we know explicitly, or unless of course we know specifically that some kind of a relationship cannot exist. For example, we might know as a rule, I don't know if this is true, but if we might know as a rule that in the universe of discourse, that in the world of movies, it is not possible for a director to be the boss of the producer or something like that. Okay, so the producer reporting to the director or whatever. So unless of course we know that some kind of relationship does not exist, we have to accept all kinds of relationships that are we might have to accept a data set which about a movie which does not contain any movie star. We might have to accept a data set where a movie contains 10 different movie stars and so on. So all such relationships should be accepted unless explicitly forbidden, and as a result the actual schema that is generated is far bigger than a typical relational schema. There are several different application areas where this is useful, and of course where these have been tried out, and these include data integration, where you design an interface to integrate different disparate data sources coming from different different locations, each having their own schematic structures. And the second major area of application is in digital libraries, where which consists of again different kinds of semi-structured data coming from different sources. Several more application areas like genome databases or scientific databases that talks about scientific documents, similar documents, citations, references, and abstracts, and where it was published, and ratings, and so on and so forth. And of course in e-commerce applications, where the discovery of structure problem becomes very important in business to business systems, where each business, if it is quite big, it might be difficult or impractical to impose a very specific schematic structure over the entire business house. So you may one needs to be able to resort to semi-structured data management when managing B2B business systems. So let us skip through these slides, where the need for discovery of structures are motivated even more, where or which talks about how discovery of structures can go about, and addressing the discovery of structures problem in itself would take a complete would involve a separate session, and it is clearly beyond the scope of this particular lecture. However, we can give some kind of thumb rules which talk about how implicit structure can be discovered from a set of disparate data sources, and most of these revolve around looking at some kind of regularity in the data set, and then generalizing based on these regularities. And so several different kinds of data mining and machine learning and artificial intelligence techniques are explored for trying to fit a structure onto a set of onto a data set. And there's also notions of what is a best fit. A best fit data structure or a schematic structure should not be too general and should neither be too specific, and so it has to be the structure discovery process should be able to generalize based on whatever examples were encountered while passing through the data. However, it shouldn't be too general in the sense that it can accept anything or any structure in the data set. That is, it should also identify what are the forbidden relationships among data elements, in addition to what are all the possible relationships among the data elements. And several different kinds of query languages are also supported for semi-structured data, in addition to XQuery, which is primarily meant for XML databases, and of course keyword based searches which are useful for full text searching. There are other kinds of primitives like navigation based queries or searching for patterns, or temporal queries based on how a particular data element evolves over time, and so on. So XML is an embodiment of semi-structured data, in the sense that XML is the natural choice in which semi-structured data can be organized, and the problem of discovery of structure or XML or semi-structured data can reduce to discovery of a XML schema given a disparate set of XML documents. And queries can be revisited using XPath and XQuery expressions based on whatever structure that have been discovered. So let us summarize whatever we learnt in this session, and of course the idea of semi-structured data in itself is a vast ocean, and it is beyond the scope of this lecture to explore all of them. So therefore we looked at native XML storage and XML publishing and different kinds of storage structures that have been proposed for XML, and mainly we touched upon the problem of the semi-structured data and the larger problem of discovery of structure, which is very important for semi-structured data management. So with that we shall end this session.